Good evening, friends. I'm Mike Knetter, and welcome to the UW Now Livestream series, where we bring you experts from the UW community talking about timely and important topics. The past few months, we've seen record-shattering temperatures, strong storms, and natural disasters across many parts of the world. What are the facts on weather and climate? And what are the major contributors to changing climate? Are property and casualty insurance markets behaving in a manner consistent with increases in severe weather events, or are they driven more by increasing home values and replacement costs? How might climate change continue to impact society, and how can humans adapt? Joining us this evening are three UW experts to discuss weather, climate, and the implications for insurance. Steve Ackerman is the Vice Chancellor for Research at UW-Madison and a professor of atmospheric and oceanic sciences. Jonathan Martin, also a professor of atmospheric and oceanic sciences. The two of them are known as the Weather Guys. They have a wildly popular show on public radio and have written columns over the years for papers around the country. And then finally joining us is UW alum Ben Wright from the American Family Insurance Group. And Ben knows a thing or two about underwriting costs and pricing homeowners insurance that he's going to share with us and give us insights into how the insurance industry has to deal with this issue. So thank you all for joining us this evening. We'll try to wrap up promptly at the top of the hour, but I really appreciate all of you taking time out of your Tuesday night to share your thoughts with our viewers. Our first speaker tonight is Steve Ackerman. He began his career at UW as a research scientist in the Cooperative Institute for Meteorological Satellite Studies. That, I think, is the largest repository of data on weather and climate in the country. And I'm sure Steve will tell us a bit about that. In 1992, he joined the Faculty of Atmospheric and Oceanic Sciences. In 1999, he became the director of the aforementioned center and led the institute through a storied period over 18 years. He's also served the campus as the associate dean and also the vice chancellor for the physical sciences. And as I noted, he's one of the Weather Guys, a monthly feature on a popular Wisconsin Public Radio call-in show. And I'm especially pleased to get Steve on the show tonight because it turns out Steve is retiring after Friday. So we didn't have time to waste to get you on here, Steve. And, you know, I just personally want to congratulate you on a really distinguished career and also just being a great colleague on the Chancellor's executive team. I've really enjoyed working with you over the years, and I'm excited to have you here with us and share your knowledge with our audience tonight. So with that, take it away, Steve.
Thanks, Mike. I appreciate hearing that. And while I'm retiring, I'm not retiring from being one of the Weather Guys. So I will continue enthusiastically participating in the Badger Talks that you do sponsor, talking about the sinking of the Edmund Fitzgerald, as well as the fact that Wisconsin is the birthplace of weather satellites. So with that, let me jump right into that and talk about what is climate. So climate is what we define as the collective state of the atmosphere for a given place over a specified interval of time. And when you look at that definition, you'll notice that there's three aspects in that definition. The first is location. So climate is defined, can be defined for the globe. It can be defined for a continent. It could be defined for a region in Wisconsin or any particular state or a city. So location is the first part. The second part of that definition is time. And that's because climate must be defined over a specified interval. So with regard to the climate of the atmosphere and weather, we look at it typically as long as a time period as we can get. When we talk about averages, we typically talk about a 30-year time period. And when we try and look at trends on how things might be changing in a particular climate of a region or the planet, we break it up into like 10-year averages as well. And then the final part of that definition is about the variable itself. We can talk about the average of a particular parameter like temperature, water vapor, pressure, winds, or we also look at the extreme values and how the extreme values might be changing. So that's the definition of what climate is. What defines a climate is the energy gains or losses of a region. So if you go to the next slide, we have a simple the diagram there of the climate of the planet. And of course, we can do this for any spatial scale. What we look at is what are the energy gains and what are the energy losses. So it's very much like us physically. If you gain too much energy, our bodies heat up. If you give off too much energy to the environment, then our bodies cool down. When we look at the planet as a whole, we're getting our energy from the sun. So that's our primary energy gain of the planet. And the way that we lose energy to the atmosphere is through infrared emission. And that is associated largely with the temperature of the object that is emitting that radiation. So that's the basic definitions that we deal with when we talk about climate. So if we're going to change climate, we have to either intentionally or unintentionally, we have to change how the planet or the region is either gaining energy or losing energy. And if you go to the next slide, one of the things where we can see where we're really impacting the climate is through how we're changing the atmospheric composition. So human activities over the years, because of how we're burning fossil fuels and other things, has increased the amount of carbon dioxide concentration. So what we're seeing there is the concentration of carbon dioxide in the atmosphere in parts per million going back from 1960 up to about 2020. And you can see there's cycles going up and down, and those cycles are associated with the seasons. So when we have more plants, less plants, that changes how much carbon dioxide is in the atmosphere. The other thing that you notice about this diagram is the trend of going from just over 310 parts per million to up to over 410 parts per million. And there's been just a steady increase in the atmospheric concentrations. Our current level of carbon dioxide levels in the atmosphere is about 416 parts per million. And we're pretty sure we'll never see levels below 400 parts per million again in our atmosphere. And again, this is just one gas associated with burning of fossil fuels. Of course, if you would expect, if you're going to be burning fossil fuels and adding carbon dioxide into the atmosphere, you might also see oxygen being taken out of the atmosphere. And we see that relationship as well. The amount of oxygen in the atmosphere is decreasing. Nothing that's going to threaten our capability to breathe and exist. But nonetheless, there's consistency there. If we go to the next slide, it's another demonstration of how we can change the energy balance of the planet or of a region. It's not just about changing the composition of the atmosphere. We can also change surface characteristics. And I think the best way to demonstrate that is to look at the urban heat islands. And so I think if you live in Madison, you know that it gets hot around the city because of the buildings that are around the cities and the absorption of the energy that they have, as well as the fact that there's not a lot of plants, so we don't have evaporation to cool, to help keep the temperature low. So what we're looking at here in this analysis is trying to look at the energy gains or the urban heat island effect, which is the temperature difference between the city and the surrounding areas that are more vegetated. And again, to try and ameliorate the effects of weather, we do this in the clear sky conditions and light wind conditions. So we're excluding precipitation, for example. And we've plotted this by the number of people within that particular city that we're looking at, the city and the region. And what you see, there are two lines, two data points. The blue is for North America and the red is for Europe. You'll see there is a difference in the slope. Both of them are increasing as you increase the number of people in the city. The European changes a little bit less. And that's just a function of the differences between some of the cities in North America, particularly the US, and the cities in Europe and the surrounding areas around them. But in both cases, what we're seeing, due to human activities and how we change the surface characteristics, in this case by building cities, what we're seeing is a bigger increase in the urban heat island. And what that's telling us is that cities are warmer than the areas around it if there weren't cities, if there were the natural conditions. So if we go to the next slide, we're going to jump to what's going on in Wisconsin. And again, what we do here is we're looking at the climate. So we're looking at the average temperature and the average precipitation. Those are the two areas I'll focus on, in particular climate regions across the state. And what we see in that yellow region, I mean, most of the state in Wisconsin, looking at the period between 1950 and 2020, that's where we have a really good record of temperature and precipitation measurements. We see that today, Wisconsin overall is about 3 degrees warmer than what it was in 1950. And that's pretty much throughout the entire state. The southeast portion of the state is not as warm, but most of the state is about 3 degrees warmer. And we can do the same thing with precipitation. Over this time period between 1950 and 2020, we have good observation of precipitation that's falling across the state of Wisconsin in those different regions. And the dark blue is about 20% increase, and the 10% is in, which is most of the southern Wisconsin. Most of the northern Wisconsin is about a 10% increase. And so what this is showing us is that today we're about 10-15% wetter than we were back in 1950. So that's sort of the overall climate of Wisconsin, which is about average. We are, of course, seeing this. It's not just in the weather data that we're looking at, but the next slide will show us something that I think if you've lived in Madison for a long time, you've been observing this, and that is the amount of ice on Lake Mendota. Lake Mendota is one of the most studied lakes in the world, and this is looking at the number of days in which Lake Mendota was ice covered. And when it's red, it's above the average, which is a little over 100. And you see that's all occurring in the 1800s. By now, when we're in the 200, 2000 and beyond, we're looking at less ice than what we saw in the earlier parts of this time period. In fact, we're almost about a week less ice than we've had in the past. So we're seeing, it's not just in the data, but we're also seeing this in the impacts that these changes have on other features like ice concentrations. If we look at the next slide, we're also looking at now the precipitation across Wisconsin. And we're looking at it again, it's for the entire state. What's the averaging period that we're looking at? The blue solid lines are annual averages. And you can see there's a lot of variability in a year to year in the amount of precipitation that we receive across the state. In order to smooth that out, we take 10-year averages and look at what is the trend that we might see when we try and smooth out and take out some of those weather variables that we might see in a particular given year. And when we do that, that's what's represented by the purple bars. You can see back in between 1900 and 1920, we were getting a little over maybe 32 inches of rain average. Now, when you look at 2010 to 2020, you can see that we're up around, it's above 35 inches of rain. So we're seeing an increase in the type of precipitation. In fact, that decade is the wettest decade that we've had on record. And it's not just about the averages. If we also look at the next slide, where we're now looking at how often does a 100-year rainfall event occur. And so we go through 100 years of the data and we look at, when in 100 years, what's the maximum rainfall? And we label that an extreme rainfall event. And what we see is what we would expect for the kind of climate and weather regime that we get. and that is in the northern regions, an extreme weather event that we might get in the Northwest is a rainfall of about 5 inches in a particular time, whereas in the Southwest region, it's more like 6 inches. If we go back to our time record in extreme rainfall over the period of just 2011 and 2020, Wisconsin has experienced at least 20 100-year rainfall events. So that's an indication that not only is the rainfall amount increasing, but it's coming in very intense convective type precipitation, so a small amount of time. So that's the overall region with regard to climate and what we're seeing in Wisconsin. We'll also want to understand how that's related to other things that we see in the atmosphere. And that's a bit about what Jon is going to be talking about. So it's not just the averages of precipitation and temperature, but also what's the impact that we're seeing and how is the atmosphere and the weather systems reacting to that.
Great. Thank you very much, Steve. That's a great way to kick our program off. And I see some good questions rolling in. One, I'll want to come back to, a viewer wonders, why do we choose 1950? They thought we might actually be colder than we were in 1930. So we'll come back to that, but let's put that in the parking lot and we'll get Jon Martin on, the other weather guy. Jon's a professor of atmospheric and oceanic sciences as well. He's a decorated, outstanding teacher, recipient of the Underkofler Excellence in Teaching Award. He is the College of Letters and Science Mark Ingram Distinguished Faculty Award holder and the Hamill Family Faculty Fellow as well. Other half of the weather guys. He is an expert in mid-latitude weather systems such as snowstorms and severe thunderstorms, and whether and how climate change contributes to these events. He's authored or co-authored more than 40 scientific publications, and he has the leading undergraduate textbook on atmospheric dynamics, mid-latitude atmospheric dynamics. That's going to be flying off the shelves tomorrow, so you better get your copy now, because before long, you won't be able to get any. Who said that? Barry Alvarez? Anyway, Jon Martin, thanks for being here tonight, and tell us what you've learned over the years about how these weather systems evolve and how they might be related to some of the climate change factors that Steve just outlined.
Yeah, thanks, Mike. Thank you for having me. And I'm happy to tell you about a little bit of a story of stumbling into a subject that I didn't really start off as an expert in. I'm more interested in winter storms. But once in a while, the winter is really boring around here, as everybody can attest. And to me, unusual compared to other people, that upsets me. That doesn't make me happy. I like to have a cold, snowy winter. So what I'm going to show a little bit about today is how the winter is actually showing across the whole northern hemisphere the fact that the climate's changing and some explanation for why that's the case. So if I can start the slides, I think we'll have some fun looking at this. One of the things that Steve mentioned in his presentation was that carbon dioxide is one of several gases that have the peculiar characteristic that they let sunlight, shortwave radiation from the sun, go right through them as if they weren't there. But when the earth heats up and radiates at a different wavelength of energy, that energy is trapped to a fair degree by the presence of carbon dioxide. And so just like anybody who knows, when they go skating on Lake Mendota or any of the smaller lakes around town, when you go skating, you find little air bubbles under the ice. Sometimes they're so big that they can give you a sprained ankle. You got to be careful. But most of the time, they're pretty small. Those air bubbles, it stands to reason, trap air at the time of the lake freezing that has the exact composition of the air around the city on that same day. So if you had access to air bubbles in ice that is historically old, such as the ice cores you can drill down at the South Pole at Vostok, and then you could take those ice cores back into the laboratory and carefully take the bubbles of air out of those pieces of ice at knowing when they were frozen, you could kind of reconstruct to a fair degree what the chemical composition of the atmosphere was on the day that ice formed. And what you're seeing here is the trace all the way back to 400,000 years ago from one of those ice cores of the carbon dioxide fraction in the Earth's atmosphere. And you can see it ranges from around 300 molecules per million molecules, that's parts per million, at the high end, to something as low as about 180 molecules per million when it's at its low ebb. And this goes way back, long before human beings had any industrialization or anything like that. And it testifies to the fact that there's a natural variation going on in the background of the carbon dioxide fraction, which in turn has a control on the global average temperature. When the carbon dioxide fraction's high, the global average temperature tends to be high, and vice versa. So the scale of these fluctuations is something on the order of 100,000 years from a peak to a peak with a valley in between. So we're talking about exceptionally long periods of time over which the carbon dioxide fraction might vary from about 300 million parts per million to something like 180. If we can go to the next slide, we can look at a close-up with even different proxies than air bubbles trapped in ice that shows something about other greenhouse gases and how they've evolved over the last 2,000 years. So the red line's the carbon dioxide, and notice that 2,000 years ago, it was around 280 parts per million. Its scale is on the left-hand side. By the time you get to the year 2000, reading the same scale, it was at 380 parts per million, so way above what it had been in the last 500,000 years. And all of that change occurred from about 1700 on, as you can see in the red line. But it's also true with methane, another greenhouse gas, and nitrous oxide, which is laughing gas, but no laughing matter. It is also a big increase in the amount that we've seen in that gas over the last 2,000 years. So let's keep going here. This is the trace that Steve showed, and I have almost the exact same numbers he has. I got this number from this March or this April. At the time, the carbon dioxide fraction measured at the top of Mauna Loa in Hawaii, which is a fairly pristine location in the Northern Hemisphere, was 419 molecules per million were carbon dioxide. And that is far above the 280 to 300 that had been the rule for the last 500,000 years. So something substantial has occurred in the last couple of hundred years in the carbon dioxide fraction. And that substantial change is the burning of fossil fuels. And there, we don't guess about how much have been burned. There's no guesswork there. It's a global industry. And any business person knows that you got to keep track of inventory. You got to know what you're going to do with what you're mining. Some of it goes to strategic petroleum reserves. Some of it goes to the market, gets burned. We know exactly how much has been burned. And as Steve pointed out, the amount of carbon dioxide increase is a hand-to-glove fit with the very small and not concerning reduction in atmospheric molecular oxygen, the kind you and I breathe. So that's a hand-to-glove fit. And we know that they're connected in a very substantial first-order way. So we got a lot more carbon dioxide in our atmosphere. So what's happened as a consequence of this big increase in this heat-trapping gas? It's like a thermostat. The higher it goes, the higher the temperature goes. Let's see some results. One interesting study, this goes back to the top part of this panel, is the carbon dioxide trace. And then the bottom part is a reconstruction of the temperature relative to the average that's current today based on isotopes of other molecules. And you can see every time the carbon dioxide fraction goes up, so too does the temperature from the past. And every time it goes down, the temperature goes down. These lines are not correlated at 100%, but they're darn close to that. So it's a pretty telling diagram. Next slide, please. We can also think about some other factors or empirical observations we can make. Jon Martin at the Limnology Institute here on campus initiated a study in 1995 whereby he collected information on lakes that have a very long history of ice duration for the season across the whole Northern Hemisphere. And he had something like 300 or so lakes, but realized that a lot of those were kind of clustered together. And so what he did is he kind of went through all of those 300 and he found 38 independent sites from among that group that were kind of widely distributed around land masses in the Northern Hemisphere. So over those 38 sites examined from 1846 to 1995, 150-year or more record, he found that the ice was getting on in 1995 about 9 days later than it had in 1846, and it was being removed by melting about 10 days earlier in 1995 than in 1846. If it were just one lake, you might have an argument as a skeptic and say, well, maybe you just had bad luck and was consistently cold or warm in that location every one of those winters. But when it's scattered over the entire Northern Hemisphere, that's a consistent and very substantial, robust signal. And let's take a look at what that means for Lake Mendota. The next slide. This is Lake Mendota's time series that Steve also showed us. The red line is a 5-year running average, and the black line is the individual years. Huge amount of one year-to-year variability. Absolutely gigantic. But there's no question that the trend is downward in how long the ice lasts in Lake Mendota. If you had money to bet on next 10 years seasons, you would not bet that it's going to go back to 120 days. You just wouldn't do that. No one would in their right mind. And an 18-day decrease which is what the Northern Hemisphere has on average experienced from 1846 to the present time, or near present time, represents about 20% of the average ice duration season on Lake Mendota. So it's a gigantic change, and it's global over the whole hemisphere. There are other hemispheric signals that are of quite interest. I think you'll see. We'll go to the next slide. Since I like the winter so much, in those years where the winter is boring in Madison, I have to look elsewhere for entertainment. One of those years was the winter of 2011 and 12. It was warm in Madison, drippy, not snowy. It was cold everywhere else. It was even cold in Tripoli, Libya. They had snow in Libya that winter, and so that drove me nuts. And I had to convince myself there's another way to get excited about the winter that's less parochial, less looking out my own window. And so here's what I settled on. This is the blue line is the -5 degree isotherm. Everywhere along that line, the temperature is the same. -5 degrees Celsius, 23 Fahrenheit, at the pressure level, 850 millibars, which is about a mile above sea level. -5 is the divider between rain and snow in most of our winter storms. And so this is why this number was in my head. But the blue shaded area is simply the areal extent of the -5 air at 850 millibars. Heart of the winter, one of the coldest days of the year, climatologically, is the 2nd of February. So every day, one could, I decided, calculate the areal extent of this cold air. And I can calculate, in other words, what the blue shading is. And if you do that, I have access to data 4 times a day, and I have 90 days in the winter, so that's 360 such calculations every winter. And we have reanalysis data sets that go back. These are real data that go back to January 1, 1948. Let's go to the next slide, Chris. This is the time series. At the top line, particularly, is the -5 degree isotherm. This is the time series from 3 different versions of these reanalyses data sets that tells us how has that December, January, February 90-day average areal extent changed since 1948. And the top line, again, -5, you can see that the trend is downward. And that trend is significant at the 99.9% level. That means there's a 1 in 1,000 chance that it's trending downward by accident and not as a consequence of something behind the curtain that's physical. And all 3 of the data sets say the same thing. So in 1948, on average, that cold pool, 850 millibar -5, occupied about 70 million square kilometers every winter. Now it occupies about 66.5 million square kilometers every winter. And that's a substantial decrease. The only way that can be decreasing is if you're eroding the warm edge of that cold pool, pushing it back poleward a little bit by retaining extra infrared energy via the carbon dioxide increase in the atmosphere. Let's keep on going. This is getting fun. Every individual year, I can look at the time series that tells me, the red line, what the areal extent is every single calendar day from December 1 to February 28th of that year. This is 1971-72. The other stuff on the diagram, the gray shading and the blue line in the middle of it is the average for every day, and the gray shading is plus and minus 1 standard deviation above or below that average. So in around February 1st, 1972, there were several days, I put green stars on them, where the areal extent of the cold air in the Northern Hemisphere was 2 standard deviations above the daily average for that time of year. And then if we go to the next slide, a more recent year, just 2 years ago, you can see in mid-December, there was a day where the areal extent on the red line was 2 standard deviations below the average for that calendar day. So I decided to just use that threshold as any day that was 2 standard deviations above the mean would be called a cold day. Any day that was 2 standard deviations below the mean would be called a warm day. And I sampled I just took a census of all the cold and warm days since 1948. We can go to the next slide. And here's the answer. On the left-hand column, 2 sigma cold events. They were really kind of front-loaded in the time series. You can see I've broken it down by decades. I don't expect you to be able to read the dates, but I can tell you that they're 100% right. And then the right-hand column is the warm events. There have been 117 days that qualify as cold events, 2 sigma cold events, and 246 days that qualify as 2 sigma warm events. Notably, not a single cold day has occurred since February 13th, 1994. And that was a week before I interviewed for the job, which this fall, I just started my 30th year here at Wisconsin. So we don't have 2 sigma cold days anymore in the winter. We have warmed up as a globe to the point where that never happens anymore. And there have been 163 warm events since the year 2000. So this is a telling story that in the depths of the winter, global warming shows its ugly head again. Let's go to one more slide, I think, for some conclusions. Over the last 74 years, the aerial extent of northern hemisphere wintertime cold pool air, that is -5 or minus 23 degrees Fahrenheit at a mile above the ground, has decreased by 4.5%. That doesn't sound like much. 4.5%. People can live with that kind of change in almost every other variable. If the sea level pressure of a day like today, 1,020 millibars, decreases by 4.5%, we're in the middle of a Category 2 hurricane. So 4.5% in the atmosphere is a substantial change. It's not to be trifled with. The shrinking cold area is absolutely a result of greenhouse warming because we're eroding on the warm edge of that cold pool. We're making it slightly warmer by extra retention of infrared energy. And finally, we're in the beginning of the Badger season. It's kind of a mixed bag so far. But if they had lost any of these games 194-0, we wouldn't even go to the next one. Extreme cold events no longer occur, while extreme warm events have flourished. The score is 194-0 since February 1994. These dice are loaded, and we see it in the data. This is not a model. This is data. So global warming's here. We don't have any time left to argue about whether that's true. What we need to argue about and put our heads together on both sides of this is what do we do about it? So that's all I have. Thanks.
Jon, we'll come back to you. I will say I was in northern Wisconsin during this thing that they called the polar vortex.
Yeah.
And I'm shocked to learn it's not a 2 sigma event. So you can tell me about that when we come back.
Yep.
But I really appreciate that. It was a great tour of the data and appreciate your perspectives. Next up this evening, we have Ben Wright, who is the Senior Vice President and Chief Underwriting Officer for Property at American Family Insurance Group. Ben leads the product development, product management, high risk, and data science teams for American Family Enterprise homeowners business. He's been with American Family for more than 22 years in roles across the actuarial, finance, product management, and product development functions. And he graduated from UW-Madison in 2002 with a BBA in actuarial science. He got out of there just in time that he didn't have to deal with me when I showed up in July of 2002 to be business dean. But Ben, you and I have had a little bit of a history together since then, and it's really great to have you on the show and hear a little bit from a business perspective about how the insurance companies and the insurance industry see these issues manifest themselves in homeowners pricing, losses, severity and frequency of storms, et cetera. So Ben, take it away.
Thanks a lot, Mike. Happy to be on the show today. As Mike mentioned during his introduction, one of the sectors most impacted by weather is the insurance industry. And the frequency and severity of natural catastrophe events is something that professionals in the industry have a keen interest in, given the impact that these events have on our policyholders and our financial results. And so today I'm going to share a bit about how climate risk has contributed to an increase in the insured residential losses that we've experienced, how that has contributed to changes in the pricing and the availability of homeowners insurance, and then finally how research and development of building materials and construction methods can help create more resilient and sustainable communities, which can lower overall loss as well as insurance premiums. And so if we move to the next slide, rising catastrophic events impact regions of the United States a little bit differently. And so the map on the left here is meant to generally illustrate the peril that various regions are most impacted by or most susceptible to. As you start on the East Coast and southern portions of the country, those are generally considered hurricane territory. As you move centrally into the country, severe convective storms become more predominant. And then finally, as you move to the western portions of the country, particularly in most recent years, wildfires have become much more predominant. And again, this is a generality. We certainly see overlap in events across these areas, such as the hurricane that recently made landfall in California. But generally, this is kind of how things hold across the country. The bar chart on the right represents U.S. residential catastrophe insured losses by year. And while some of this increase that you observe here can be attributed to population growth and inflation, there's an undeniable trend present here that is driven at least in part by the frequency and severity of various catastrophes over the past 25 years. And you can see here material increases in the aggregate losses across each of the major perils shown, in particular over the last several years. A couple things to note. One, aggregate wildfire losses in the past 6 years were higher than aggregate wildfire losses across the prior 20. Wildfire were something, in my childhood at least, didn't hear a lot about. But in more recent years, we've seen a lot of press around wildfires and a lot of investment in the industry around that, which I'll talk about in a little bit. 5 of the past 6 years have had aggregate hurricane and tropical storm losses in excess of $10 billion. And then while severe convective storms certainly don't get the headlines, they've produced more than $10 billion in aggregate losses from a residential perspective in 5 of the past 6 years, and 2 of those years actually being more than $20 billion of loss. And so moving to the next slide, unfortunately, the trend of significant catastrophe-related losses on the insurance side have continued into 2023. The first half of this year, there were 18 events that generated more than $1 billion of insured losses across all lines of insurance. And that's compared to an average of 7 in the prior years since the year 2000. Total insured losses in the U.S. during the first half of this year reached at least $40 billion. That's the 3rd highest year on record after 2011 and 2021, and likely will keep developing up as more claims are reported and settled. I mentioned earlier that severe convective storms don't necessarily get the catchy headlines. That said, they're capable of producing a massive amount of loss. This year, in the first half of the year, 9 of the top 10 global costliest insurance events were severe convective storms in the Midwest. You can see 5 of those listed here in terms of the date that they occurred, each of which produced between $2.5 and $5 billion of loss across all impacted lines of insurance. And so suffice to say, it's been a very active weather year and one that's likely to continue in the remaining months of the year. Moving to the next slide, to start, I would say that the good news here is that broadly, the insurance industry has consistently met their obligations to their policyholders and what has been some of their greatest time of need. And so even though we've had a huge ramp up in losses related to weather events, we've been there in our customers' times of need and been able to meet our obligations. That said, this increase in losses from natural disasters over the past several years has caused insurance carriers to increase their investment in what I'd characterize as risk management activities, or activities that are aimed at helping improve financial performance to help ensure that industry carriers continue to be there for their policyholders long term. And so a handful of those activities are listed here that some carriers have chosen to implement as part of their risk management strategies. To start, and some of you may have observed this on your home insurance policies, some carriers have instituted policy changes such as increased deductibles or actual cash value roof settlement to help mitigate some of the loss impact from storms. Inflation has made smaller flat deductibles less impactful than they were historically. And so higher deductibles help avoid smaller claims or issues that are more related to maintenance, while also helping keep premiums down and keep them more affordable. Roofs deteriorate over time, and the value associated with an old roof is much lower than a newer roof. And so actual cash value here means that a depreciation amount is applied to the claims payment starting after a roof reaches a certain age, typically 10 or 15 years. And this is intended to reinforce that insurance is not a substitute for maintenance, with old roofs providing much less protection to a home when it comes to the elements than a newer roof does. Additionally, many carriers have ramped up investments in improvements to catastrophe modeling and increasing prices based in cat-prone areas. And so from a catastrophe modeling perspective, improvements in predictions related to catastrophic events allow carriers to improve their ability to match price to risk, meaning allowing them to offer customers a price that is more commensurate with the risk that their properties present. Historically, what we've seen from a catastrophe modeling perspective is that model miss is on the low side, meaning that the losses that these models estimate generally have been lower than what we've actually experienced. And so there's been lots of effort taken to improve those models and improve how we use those models to ensure that we have more accurate forecasts. Also, almost all homeowners have likely seen their insurance premiums increase materially over the past couple of years. Increased risk of catastrophe losses certainly has played a role in this, along with the rapid inflation that we've seen in reconstruction costs since the onset of the COVID pandemic. Finally, some carriers have also increased utilization of risk-sharing tools such as reinsurance and cat bonds. Reinsurance can be thought of as insurance for insurance companies, and it's a way of transferring some of the risk that they have to other insurance companies, and that helps reduce the impact on the organization from certain catastrophic events. A cat bond is a high-yield debt instrument that is designed to raise money for companies in the insurance industry in the event of a natural disaster. The cat bond allows the issuer to receive funding from the bond only if specific conditions occur, typically related to a specific type of catastrophic event and then a certain amount of loss occurring. If an event protected by the bond activates a payout to the insurance company, the obligation for that carrier to pay interest and repay principal is typically either then deferred or completely forgiven. And I should say then finally, some carriers have also chosen to restrict underwriting eligibility, meaning they've chosen to no longer offer insurance for certain types of risk and reduce the availability of their insurance in the market. Most everyone has likely heard about California and Florida being prime examples of this, where a number of carriers have restricted their appetite, largely because they currently feel they can't get a premium that's commensurate with the risk. I'll say that these states are atypical. They present unique challenges and are not the norm across the country. And generally speaking, I wouldn't expect availability restrictions that exist in those two states to start to spread more broadly across the country. Moving to the next slide. And so while there are a lot of challenges here, I think it's important to note that improving building methods and materials can greatly reduce the loss associated with weather-related events and ultimately reduce insurance costs. There are building certifications such as Fortified by IBHS that have been shown to materially improve resilience, oftentimes for a relatively small incremental increase in construction costs. And this doesn't have to apply just to new homes. There's certain retrofitting improvements that are possible even on older homes, such as selecting and installing roofing designed to withstand wind and windblown materials, withstand hail, adding hurricane shutters to windows to protect the glass from windblown debris, and taking steps to reduce the risk of ice dams on your homes, such as promoting overall attic ventilation and improving the airflow at the eave between the roof deck and the attic. And so there are a number of improvements that can be made to homes to help them withstand these sorts of events. Generally, a lot of research has gone into building resistance in sustainable homes. The insurance industry has been a large contributor of that, with a vested interest in terms of helping their policyholders reduce the impacts to them of catastrophic events while also reducing loss. And so there's been some great developments in this space. And if we move to the next slide, we can see a real world example of this. And so this is a photo after Hurricane Ian, which occurred last year, which was sourced by the Insurance Journal. And this photo shows damage in a neighborhood along the coast of Florida after Hurricane Ian came through. And you can observe a significant amount of destruction in this neighborhood. But in particular, you'll see this one home up right on the coast on the right-hand side along the top that is still standing and honestly appears to be relatively unscathed. And this home was built much more recently when codes have been updated with some of the standards that were represented on the prior slide, and ultimately was able to withstand this hurricane to a much greater degree than homes that were built in prior decades, which are noted on this picture as well. And so you can see this as a great example of how these newer construction methods can help create much more resilient homes and ultimately allow people to reside in these areas that are much more prone to catastrophes than maybe were historically. And so on this last side, on the next slide here, just finally wanted to provide some links if you're interested in learning more about insurance and catastrophes. There's 3 organizations here that some of the materials here I've sourced, but that I've gone back to myself, my team has, and many in the industry to inform ourselves about what's happening within the market, as well as things like construction standards and weather trends. The Insurance Information Institute, or III, was established in 1960 and has been a trusted source with unique data and data-driven insights on insurance for many decades, and have a wealth of information on insurance. The Insurance Institute for Business and Home Safety is an independent nonprofit scientific research and communication organization. It's supported by the insurance industry and affiliates, and conducts a plethora of research around construction methods and building materials, and provide sound advice and standards for builders to adhere to that can help, really withstand weather-related events. And then finally, NOAA, the National Oceanic and Atmospheric Administration, is a great source for climate and weather information in general. It's most certainly not insurance specific, but the information that NOAA collects and provides is something that a lot of top carriers use today when it comes to assessing climate risk and ultimately establishing rates and underwriting rules related to the risks that we insure.
Ben, thank you very much for that tour through how this all looks from the insurance industry perspective. I want to go to audience questions. And before I do that, I just want to acknowledge at the outset, there are very different views about the evidence on climate and weather. And, the Pew Research Foundation certainly finds that there's still a high fraction of Americans who are kind of, let's say, climate skeptics. A majority certainly believe that climate change is real and is happening and is producing some of these severe weather events. But I want to be respectful of all points of view. And the thing that we know from just political polarization is that views on both sides have kind of hardened on what the facts are. So I want to unpack a little bit of the data that we talked about tonight. I always think back, we all know science evolves. We do research, we measure things, we have debates, we have an understanding of the world at one point in time, and sometimes 10 years later it's different. And on environmental issues, I often think back to that famous Julian Simon Paul Ehrlich wager that was made in 1980. Paul Ehrlich is the biologist who wrote the book Population Bomb, and he thought all commodity prices would be going up. And a business professor, Julian Simon, bet him, you get to pick the commodities, and I'll bet they'll go down in price over the next, whatever period of time you want to bet on. And, Julian Simon proved to be right. The commodity prices did go down, which wasn't what Ehrlich thought would happen. I'm not sure that's still true today, but it happens. And so I think we always have to have a certain humility about what we do. So I want to go back and ask Steve a question that I kind of foreshadowed. When we pick these periods of time to analyze, from 1950 to the present, what happened, how sensitive are they to endpoints? I've published research papers in my own career, and I've never had a referee who didn't try to beat on me about, whether my sample was typical or not. And, it's very hard to get something published if you haven't considered the robustness of the result. How robust is your observation, for example, about Wisconsin being 3 degrees Fahrenheit warmer and 20% wetter than it was in 1950 if we change the starting point or the end point? Is it a steady trend, or is it really volatile?
That's a good question, Mike. And I think the thing we want to be careful about, and why that time period changes, because we want to make sure that we have accurate observations during that time period. And so if you look at a particular area where you only have 1 or 2 measurements that are really accurate and well-calibrated instruments, then that's going to limit the length of your time period. When you go to really large time periods, and we showed some figures associated with that, some of that data is not necessarily instrument data, but it's looking at other geographical features of where glaciers might have been and things like that. So that time period of where we're at is really a function of quality of the data. If you don't have a good set of data, a high quality data set, then you really don't want to extend beyond that time period. And then the other thing I'll add is we look at this time period. Sometimes we also move it around because we're not just looking at, for example, temperature. If we look at temperature, we see it's warming, then we would expect certain things to happen, like more rain, right? And so we're always looking to make sure that those time periods between different parameters are also consistent in terms of accuracy in those measurements. And we have a pretty hard standard definition of high confidence, middle confidence, low confidence in the data and in the analysis of that data. I don't know, John, you want to add anything?
I'd say along the lines of what you just said, there was a time between the second and third IPCC global report where they convened an adverb committee to decide ahead of time what various adverbs were going to mean when you would shade what you thought was the case after 1,000 people had kind of argued about this. What does likely mean? What does very likely mean? What does extremely likely mean? And so, I mean, that's talk about one of the circles of hell, serving on an adverb committee. But how extremely smart that was. No one could accuse the IPCC of jury rigging the words they used. They did it beforehand they ever used any of them. And so now we're at the point where it is unequivocal that human beings have so changed the chemical composition of the atmosphere as to have engendered these changes in the last 100 or 150 years. That's now unequivocal. And in 1995, when the second IPCC report came out, it was a vanilla statement. It said, the balance of the evidence suggests that human activity has had a role to play since 1900. So we've been skeptical of ourselves. Scientists eat each other up with skepticism. And yet, in spite of that, the refined views that come from more and more analysis and more observations leads you to an unequivocal statement in 2023.
Yes, certainly the loud climate deniers, if they are proven correct, will become very famous. And there's always an incentive to be a contrarian in science and poke at received wisdom. That's really what it's all about. John, I want to come back to you because in 2020, I bought my first and only striker ice fishing suit with bibs and everything else because it was so damn cold during the polar vortex. Yeah. And maybe it wasn't 2020, but the polar vortex came down on Wisconsin really hard. And you were saying we've had no 2 sigma cold events since 94. Yeah,
that's right. Keep in mind, Mike, my analysis is for the whole Northern Hemisphere, not a single region of it. So that's where the out is. So it would be like saying the major leagues have never had a 60 home run season since 1927. Not that an individual player hasn't. So it's that kind of a distinction. So it takes a lot to get the globe, the whole Northern Hemisphere, to have a 2 sigma event. Doesn't necessarily take a region that much, and they will still happen in a warming environment.
Got it. Okay, that helps. Steve, I want to come back to you on something. When you talked about climate, and you mentioned, we've got several dimensions that we look at when we measure climate: temperature, precipitation, pressure, wind, all these things. I'm an economist, so I look at kind of volatility in the markets. They've got a statistic called the VIX, and they just report on the VIX on a regular basis. And everybody knows what that means. It's the kind of the standard deviation of, price volatility, intraday, intra-week, whatever you want to measure it at. Do we have kind of standard metrics about climate where we take maybe a long, like a 30-year moving average of temperature or this variable, that variable, and try to look at, is there an analog of the VIX that climate scientists use that show that, not just averages or extremes, but actually in between there, the variances or standard deviations are really higher and we see more extremes?
Yeah, so we do look at standard deviations when we average over a decade or a 30-year period. And that's to try and get at the sense of what is the quality of the data. The other thing that we're also looking at is consistency between data records. So when we're looking at a temperature record and a precipitation record, we're also expecting some sort of physical relationships between those parameters. And so I'm not sure it's quite as an index as it is a physical understanding of what, as one changes, what would the other one look like, the other weather parameter look like in response to that change? And then how does that change to other things like the sea ice on the lakes? If you expect the temperature to warm up and you're seeing the lake temperatures to warm up, well, you ought to see then a less ice on northern hemisphere lakes. And then you go and you look at that and you see that, yep, that's physically consistent. But I don't know, John, do we have, I can't think of any specific indexes that
well,
we
I
would
did
look
that.
at in
You know, I
terms
showed in my slides, I showed a couple of the annual time series of the cold pool aerial extent from
of-
day
That's
to day.
true. Yeah.
And I have 74 years there, and I did a volatility analysis on that, Mike, exactly along the lines of what you do with the market, with indices in the market. And one thing I can tell you is that it did, at least in 74 years, there doesn't seem to be any increasing trend in volatility. But there is a distinction to be made between the years that have a volatile cold pool and those that don't. They do seem to have some substantial environmental differences. That's interesting, but there doesn't seem to be a trend in increasing or decreasing volatility. But we maybe not have a long enough time series. Could be interesting to keep an eye on that as years go by.
The Wisconsin Climate VIX Index. I can see it.
Yeah, it's kind of.
We better start working on that.
Right.
All
Exactly.
right, I'll meet you at Encore for coffee. We'll talk about it. Ben Wright, I got a question for you from Nancy Aronson. We're not going to leave you out of this. Will we see insurance companies leave markets and regions with a disproportionately high amount of natural disasters, wildfires, et cetera? I think I know the answer to that already.
Yeah, I think, there's certainly some carriers that will choose, at least in the near term, to exit some regions where they feel that they just don't have the pricing and the underwriting tools to effectively place the risk with them. I think broadly, though, we'll see insurance availability across the country. There are hundreds and hundreds of insurance carriers. And while some may have to step away because they haven't managed their financial results or their exposure appropriately, I think there'll be others there ultimately to fill in that gap. But I think in the near term, you're most certainly going to see increases in prices and restrictions and availability until the market can reconcile with some of the changes that have occurred.
Great, thank you. We are coming up on the top of the hour, and I promised you we'd wrap by 8 o'clock. I guess, in light of some of what we've spoken about tonight, I don't know, Steve, and then John, and then Ben in order, if you have any final thoughts that you'd like to share about, what you see going forward for climate, weather, insurance markets. Steve?
Yeah, I think we're going to continue to see what we have been seeing unless our habits as humans change, and that we're going to continue to see a change in our climate system. And simple metrics of that is what temperature is. And we're going to continue to see trends in increasing global temperatures and regional temperatures.
John?
Yeah, I'd just say, Mike, that I realize there are some people out there, some of them are friends of mine, who are skeptical about whether or not the science is so conclusive on this, the current state and the immediate future state of our globe. But to them, I would say, let's stop arguing about that and start arguing in the constructive way about what we're going to do about it. And all minds have to be on deck on this. So we need people who are not so interested in green solutions arguing and discussing things with people who are, to make sure that no single agenda takes the future away from us, but that we build something constructive with all of the different perspectives that we bring to that. And so I'm very respectful of that conversation, but I think that's the conversation we have to have now. We got to stop wasting our time arguing about whether or not the climate's changing. It is, and it's our fault. So we got to do something about it.
Yeah, from an insurance perspective, we expect insurance losses related to weather events to continue to increase at a pretty rapid pace. We don't see a ton of argument internally about that anymore. Instead, it's more about what actions are we going to take to address that. I think you'll see a few things in terms of, one, prices will most certainly go up. You'll see continued investment in catastrophe models so that we can better forecast and predict what's going to happen in the future and price appropriately. And then secondly, you'll see the industry continuing to partner with research firms and states to promote resilient and sustainable construction methods and building materials to help ensure that, one, we can continue to offer insurance in these areas and that people can continue to reside in the places that they've historically lived and worked.
Great. Well, look, we're at the top of the hour. I just want to thank all three of you for joining us tonight. We've got a risk of severe weather in Madison this evening, and I'm glad we were able to get our show in without losing power here. And just really appreciate you all bringing your expertise to our audience. And our audience, there are a lot of great comments and questions tonight. I realize not everyone sees this issue the same way. And, I tend to go back to, these CAT models in the insurance industry, which does spend a lot of money on trying to understand this issue, a lot of money. They have a lot riding on it. And the models continually underpredict what the CAT losses are likely to be. And that's somewhat telling. And I guess whether that is a sustained change that's driven by man-made causes or kind of a secular trend that might reverse itself, we may not know that yet, but I think the evidence is kind of mounting in one direction, and we'll see where that goes. But we'll stay on top of this issue, and I just thank everyone for joining us this evening. We'll be back again with another live stream on Tuesday, October 10th. Thanks for joining us this evening, and on Wisconsin.
In 1848, just 2 months after the creation of our beloved state, a great university was born, the University of Wisconsin, to serve, educate, and benefit people from every corner of Wisconsin and beyond. And for 175 years, we have pushed forward, energizing dreams and igniting innovation. With educational opportunities that create promise and research that improves lives, UW-Madison is a place where an idea can change the world. And as we look forward, we also look back to stand up for what's right, build common bonds, and a better future. When combined with inspired goofiness and Badger spirit, there's an inspirational and unconventional vibe that's all Madison. It's more than just fun and games, though. At the UW, we go from brainstorms to breakthroughs, from today's students to tomorrow's leaders. This is where an idea can change the world, the whole world, a corner of the world, my world, our world. UW-Madison's profound eurekas and personal ahas transform us all and serve the greater good. As proud Badgers, we celebrate the last 175 years and the next as the UW charges forward. On Wisconsin.